Hello, I'm here to talk about the Oregon Country Fair and some of the technical challenges that we've had with communications there. And in order to understand the challenges, you need to understand what the Oregon Country Fair is. It's not your typical county fair with livestock auctions and a tilt-a-whirl. The Oregon Country Fair started off as a Renaissance fair in 1969. It's located near Veneta, Oregon, about 15 miles west of Eugene. And the main venue is in a wooded area bounded on the east by the Long Tom River, and on the west is where a lot of the parking and infrastructure is. It's known as the 8 because in the woods there is a figure-8 shaped path there. It's about 28 acres. And this has grown substantially over the 50 years that it's been in operation. It's held on a 3-day weekend, Friday, Saturday, and Sunday. Gets about 22,000 visitors each day. And in addition to music and stages and parades, there are about 900 craft booths selling various handcrafted artifacts as well as food booths. And it's a very elite type of crafts. Anybody who wants to present there has got to go through a peer-reviewed jury to approve their crafts. It's nonprofit with somewhat limited funds. One of the problems is that the 8 parts of it flood when the Long Tom River overflows its banks in the winter. This is typically what it looks like when the fair is open, and this is what it looks like in the wintertime. Those are the various crafts booths and what have you. So it makes a permanent infrastructure a little bit difficult. There is no grid power in most of the 8. There is grid power on the west side. Communications, the staff extensively uses two-way radio, walkie-talkies with repeaters. There's a landline analog PBX, affectionately known as Tinkerbell, that has analog phones spread throughout the area with the wiring run through the trees. Again, very limited availability of grid power. And we have excellent cellular service 362 days out of the year. As I mentioned, we're a 3-day festival. The internet is supplied by 5 bonded ADSL lines during the fair. That's basically all we can really get. There is no cable infrastructure to the area, and so that's what we're limited to. When the off hours, we reduce that to 2, and then during the fair, we step that up to 5. So we have an aggregate bandwidth of about 20 megs to the entire facility. The cellular infrastructure is designed for the nearby town of Veneta, has about 4,500 people. And most of the time, those people are going to be in their homes or offices on their local Wi-Fi and not using the cellular network. When you take 22,000 visitors and put them in a 28-acre area served by one cell site, the cellular network basically melts. You're lucky to get 1 out of about 4 or 5 phone calls through. If you send a text message, you might get it anywhere from 15 minutes to a couple of hours later, and just forget cellular data. There is a need for the staff to use internet wirelessly, but the primary problem that we're trying to solve is the vendors that need connectivity to process payment cards. The initial Wi-Fi deployment, which set up several years ago, has a 900 megahertz backbone between 2 hub locations and 7 different repeaters located in trees. We use 900 megs because it penetrates the foliage very well, and then we have an omni antenna in the tree that broadcasts 2.4 gig to the users. And these are powered by 12-volt storage batteries, basically a couple of large car batteries at the base of the tree during the fair hours. And this has been in place for the past several years. There you can see one of the trees and then a close-up of the 2.4 gig antenna, and you can barely make out the dish near the oval there. And this Wi-Fi serves multiple uses. During the public hours, again, the vendor access to payment processing is critical, and that's prioritized. The vendors are on their own password-protected SSID. The staff uses a separate SSID over the same infrastructure for administrative needs. And then during non-public hours, we turn up a third SSID for volunteers and others, just basically to use the internet. The firewall and QoS is controlled by pfSense routers at the hub. And over time, the vendor needs for processing payment cards have become more and more critical. The craft booths are putting out some fairly expensive items, and more people are using credit cards. There's a limited availability for ATMs. They need to be where the grid power is, and they also need communication. There are a couple of ATMs on site, but they are on the west edge where we have grid power, and they're connected by a wire line back to the LEC. And what's happened in the recent days is that small business merchant accounts are now much easier to get than they were in the old days. So everybody has got a cell phone app with a Stripe or a Square reader that reads the chip cards or a Stripe. Customers are preferring to pay by card, and the offline transactions are risky for the merchants because you don't know if it's a good card. So the driver for what we're trying to do is to allow the merchants to process their payment cards. And one of the things we found is that you give a merchant a password for their SSID for merchant processing, and when sales are slow, they're streaming YouTube and doing other things, and that tends to overwhelm our 20 megahertz or 20 megabit connection. So even if the vendors don't abuse it, we have found that cell phones are extremely chatty. And they're even more chatty on Wi-Fi than they are on the cell network. So all these background apps refreshing, people trying to find out your location to send you ads and what have you, the cell networks. All of these apps on the phones are creating quite a bit of noise. We started off using a whitelist, and surprisingly, you can call up the various payment processors and say, hey, what IP addresses do you use? And they're very happy to tell you. So we started off with a whitelist of IPs of the well-known payment processing and only allowed those. Anything else was directed to a static page that basically said, go away. And the whitelist, we found some issues with. The primary well-used payment processors are all in there. But occasionally they might have part of their infrastructure that's served by a CDN that might be the same CDN that's serving other things that we don't want. So we've changed recently to a blacklist where essentially we have opened up the vendor network and we're running netstat looking at the top talkers, and then as we find the abusers, we throw those into the blacklist and route those to our static page. And this seems to be working well and is scalable as more and more, as we start to reduce the noise, the other ones start to bubble up. And of course, every year we discover that there are new apps and new things that we need to put on the blacklist. The drawbacks of the current wireless system, it works very well for staff use outside of public hours. But being 2.4 with 22,000 visitors on site, a lot of them are running ad hoc networks that are trying to tether devices to the very poorly performing cellular network. And so there's quite a bit of noise in the 2.4 gig band. We also have what's called the hidden node problem. So when you put a repeater high up in a tree, it's looking at a large area of the fair. And so it sees all of these low-to-the-ground radios, but they may not see each other. So if you have a user with a radio that is will interfere with another user because it doesn't see that other user and know that the channel is busy. There are some protocols within Wi-Fi to try to limit this hidden node problem, but it's not perfect. And during the public hours, these 7 repeaters tend to get overwhelmed. The other problem is that it is a wooded area. The foliage causes dead spots, and it aggravates this hidden node problem. You might be right under a repeater, but the trees block you, and so you're connecting to one that's further away. and then labor-intensive, having to go out to these various repeater sites and change the batteries periodically as they get depleted is a problem. So the problems we need to solve: 2.4 gig wide area radios are not usable, and we really need to reduce the coverage area per access point, which results in obviously needing many more access points. We've looked at 5 gigs. The 5 gig band is now available on virtually all of the modern smartphones and devices that are used for payment processing. And the foliage limits the range substantially, which can be a good thing for us, because the limited range means that you're not going to have as much of a hidden node problem, in that the radios will only talk to a small area. In 2016, on the west end of the fair area, we deployed a pilot project where we did have grid power available and ran 3 5 gigahertz radios connected back to via wired Ethernet back to the hub. And this worked very, very well. The people in that area were able to access the internet and get their credit cards processed. So the small low-to-the-ground 5 gigahertz project did show some promise, but did not solve the problem of power and being able to extend this network into the rest of the area. And surprisingly, the cable companies, and those of you who are in the cable business, this is going to be old hat to you, but the 75 ohm coax cable backbone that's used by cable providers has a very interesting feature, in that in the field on the cable, there are amplifiers that are needed to take this signal a long ways, and those amplifiers need to be powered, and they're typically in the middle of nowhere on a span on a telephone pole or something. So what the cable people do is they have a power supply that injects AC voltage onto the cable. It's very wideband. We created these devices called a node, which is essentially, rather than using the power to power a trunk amplifier or a fiber to coaxial converter, we use that cable power to light up a box that can handle the access points. This eliminates the need for swapping batteries. The cable plant is designed to be environmentally rugged. It's out in the rain for years. And it's expandable by either tapping the cable line or extending it. At the head end, or the hub, we have what's called a CMTS router, which is a cable modem termination system that converts our Ethernet to coax. And the way this works is the high frequency, which is a legacy from the analog television networks, anything basically above 54 megahertz on the cable, is used downstream from the hub to the nodes and to the radios. And then lower frequency than that is used for the upstream data. At the head end, there's a device called a diplexer, which combines these high and low frequencies onto the cable, and then there's a power injector, which has an isolated 90 volts AC that's fed down the cable. In the field, when we want to drop a node, there's a device called a directional tap. And this is, again, standard cable technology. This takes a small amount of the signal and routes that to the node and sends the rest down the line. And it also optionally can provide the AC power. At the end of the line, there's a terminating resistor, basically to avoid reflections and nasty things that can happen with RF when you have an unterminated line. This is basically what the system looks like schematically. The red arrows are the downstream data coming from the internet going out to the customer radios, and the blue is upstream coming from the customer radios back to the internet. Power is injected with the green line from the power injector. The items on the left hand of the screen are at the hub, and then those at the right hand of the screen are out in the field. So each area node is powered from the cable trunk line. It then basically has a power inserter working in reverse to strip this 90 volts from the cable line before passing it to the cable modem. There's an auto transformer that is used to step that 90 volts back up to 120 to power the gear within the node. Because the cable plant is designed to power hundreds of cable modems, and we're only typically having less than 10 on a device, the RF levels are extremely high, So we put an attenuator in to bring the radio frequency levels down to what's appropriate for that node. And the value of that attenuator depends on how far away from the hub we go. Those that are close, we reduce the signal quite a bit. And then as the cable attenuation is extended, and as we're dropping more power from other nodes, we reduce the value of that attenuator to the appropriate value for the modem. And then also within the node is a power over Ethernet router that is used to deliver the power and the data to the radios. And each node can have up to 4 radios that can be extended the typical 100-meter distance of Ethernet from that node. And these are directional 5 gigahertz access points. Schematically, this is what the node looks like. We have the cable coming in, take that power inserter in reverse, run that through the auto transformer, and that's used to power the cable modem and the router. And then the signal is converted from the cable modem back to Ethernet, lights up the router, which then powers the radios. And each node with 4 radios pulls about 70 watts. With the 90 meg at 10 amps, we can run up to 10 nodes, a little over 10 nodes on a cable line. This is basically what the node looks like internally. The cable's coming in on the upper right. The power injector or power stripper is then applied. You see the red and white wires coming there, the auto transformer, and that then powers the cable modem and the router. And then we have the Ethernet out going to the radios. This is in a NEMA 4X box that is weatherproof. And this is what one looks like deployed out in the field. You can see the directional coupler and the node box out in the field. This particular one happens to be at the end of the line, so you'll see that device on the lower right-hand side is the terminating resistor. So we found that this technology really works to deliver Wi-Fi to a small area and is extendable. And here is that same shot that we saw earlier, and if you look at the circle there, that's one of our stealth radios. These are ubiquity access points that we've camouflaged. We don't generally like to advertise the technology to the people at the fair, so we try to keep it stealth, but on the other hand, make it usable. So in the future, we're going to expand the cable nodes, adding more as we go along. Finally, we are able to get some real broadband to the fair. Not sure if that's going to be fiber or coax, but we should be able to get in the 100 megabit downstream, hoping to have that for the 50th anniversary coming up this July. And we continue to tune the firewall and QoS as we try to filter out everything other than payment cards on the vendor network. Presently, we've got a second-hand cable router, the CMTS, and it is using a card that is only capable of a single channel. It's DOCSIS 2.0, and that gives us basically a maximum of 35 megabits per cable. And now that DOCSIS 3.1 is out, I'm hoping that the 88V cards that support DOCSIS 3.0 with wider bandwidth will drop in price before the fair this year, and we can just basically drop that in and get some more bandwidth. So this seems to be working very well, and that's what we're looking forward going forward. Are there any questions?
Hi, I'm Jeff Haas. I'm with Juniper. Question for you about your list. Did you consider just simply rate limiting the traffic? So instead of trying to play whack-a-mole with all the addresses, just crank it down so that you only can get trickle traffic through. The credit card processing would behave perfectly fine, and the minute they try streaming, they're going to be so unhappy with it, they're going to stop it.
We looked into that a little bit. The problem is that, again, we're limited to a maximum of 20 megabits per second for everything, and the background apps on the cell phones, even though its per user is relatively small, that noise is just there all the time. And keep in mind, we've got roughly 900 vendors that are using this in this small area. So it just made more sense to us to basically knock down the top talkers of the Netflix, the YouTube, the Facebook, and what have you, and as they pop up and we see, oh, look, now this is the new top talker that is getting through, and we add that. So it's difficult to do that just because there's so much and it's so varied. Every single app that's got a background refresh is going somewhere else.
Okay, thank you.
Hi, Rob Seastrom. I used to work for a really big cable company, and now I don't anymore.
Okay.
This is really cute. I like this. And one of the things I noticed is that it looks like you used RG11 and not cable hardline, because you don't have a really long plant. And that's nice, because it means you don't need special weird tooling or anything, and you can keep the costs in check, because hardline is really expensive.
Yeah, the RG11, going through the trees, it's a lot easier. If you kink that hard line, it's a problem. And
Yeah.
that was near the end of the path. We are deploying this year some half-inch hard line, which has got a 14-gauge center conductor as opposed to the 16-gauge on the RG11. Again, with the frequencies that we're using, we don't really need a lot of
So yeah, that was one of the things I was going to point out, is you've managed to keep your downstream channel somewhere, low, as
Yes,
opposed to
exactly, yeah.
traditionally people find it up around 600 megahertz,
Right, well,
because that was the place that was already open when you went
Yeah.
beyond the 500
and
megahertz cable.
Yeah, there's no local TV channel 4, so
Yep.
that's what we're using
Yep.
for our downstream, and that also.
So,
Yeah.
so that brings me to a point. I'm hoping that somebody will not hop in line and tell me that my memory is completely nuts. But if you, I'm thinking back to the days before DOCSIS 3.0 actually rolled out. I think as long as you keep your upstream separate and your downstream separate, you may be able to get away with running 2 D3.0 cards into the same cable plant in parallel, and having when the modems range, having them stochastically join to one or the other.
We haven't tried that. We haven't needed it. Again, the overall bandwidth to the entire facility is less than we can get on a single
Yep.
6 megahertz TV channel.
Yeah, I hear you, but you're going to be getting.
We're going to be getting more.
Going to be getting fiber, and
Yeah.
last I checked, the D3.0 stuff was still actually a little pricey compared to.
It is. I'm hoping
D2.0, which you
3.1
can
will
pull out of
drive
the
that
dumpster.
price down.
Awesome. Thank you.
Joel Yegley, 2 questions. There's some kind of rural overbuild that eventually gets fiber connectivity out to Veneta, I suppose. Is that something you see as making this sort of facility easier? Is CenturyLink or Quest actually building facilities out to places where you need them? Or is that not something that's
Well, that's what's
still
happening. That's why we're thinking this year we've actually placed an order to get connectivity. Getting fiber connectivity to our infrastructure is something that we're very much looking forward to. But again, running fiber out to the facilities where the people are, we still have the power problem.
Yeah.
So this seems to be a good compromise of ability to do that. I might add that the cellular people did put up a couple of cell on wheels. AT&T and T-Mobile came out and put up cell on wheels for this event. And that helped some, but they was still pretty much overwhelmed.
So they do microwave backhaul for those or something?
I don't know what they're using for, they may be microwave, I don't know.
Yeah. The other thing that looked really cool here is you have a stable of crusty old radio engineers. I think Ichabod may be the crustiest one.
Yes,
but,
yes.
You've essentially used a technology that is mostly compatible with their view of the world, which, that's definitely leveraging your strengths there.
Yeah, we do try to hide the technology from the fairgoers, but there are a lot of high-tech geeks that are part of the infrastructure of the fair.
Yep.
Of the
Very
volunteers.
cool.
Adam Mills from Roblox. I had a question about how many, you mentioned that there are modems and routers and then the antennas. How many of those devices are you currently managing? I saw that you're using the Ubiquiti PoE. Do you leverage their automation for that, like their Unify?
No, actually,
application?
we flash the radios with OpenWrt.
Oh.
So we're not using the ubiquity radio configuration. We're using OpenWrt, and that allows us to, in an automated manner, push changes to the radios, such as changing the passwords, enabling or disabling the SSIDs outside of the public areas.
And then how many do you have currently deployed?
We have the 7 repeaters, and then we have 3 nodes, each one of which has 3 radios, and the other 2 have 4 radios.
Thank you.
And this year we'll be adding more. Okay, thank you very much.